finished after the coffee break. It's now time for the second of these two related talks to be given by Nigel Mottram from Strathclyde. Over to you.
Okay, thank you, Mike. This is on. Is this on? Yeah. So, just before I start, I've got two adverts I've been asked to make. One is for the British Liquid Crystal Society conference, so people might have seen this before. So this is next week. It's in Cambridge. It's only 500 yards away. So if you're here next week, then please come along. You can register at this website, which you can quickly take down, or you can just Google BLCS 2013, and you'll find out all the details. The second one I've been sent from the ICMS, the International Centre for Mathematical Sciences in Scotland. This is a kind of mini Isaac Newton Institute almost. Scotland's only 10% of the UK, so we have a kind of small Isaac Newton Institute up there. And I thought this might be useful, might be interesting to some people who are here during June, differential geometry and continuum mechanics, and some extremely famous speakers. Oh, and Epifanio Berger as well here as well. Okay, so just acknowledgements before I forget. So this is many different projects all put into one talk. It started out with a PhD project, which is purely theoretical, and eventually led to patents and various funding from different areas. It started theoretical, but then I have to be slightly careful because I think possibly Carl Brown is watching at this moment online. So I'm sorry, Carl. But we eventually, some experimentalists became involved. We wanted to create this device for real rather than just in a computer or theoretically in equations. And that's great. And that's great in some ways because they can realize exactly what you want or tell you where it goes wrong or how to improve. The main problem is, and this is kind of a big thing about this talk, is that when you're working with experimentalists and all this industry as well, they do things really fast. I mean, the problem is they can create these devices and test them through a vast array of different parameters very fast. And anything you do theoretically that's going to be of use to them has to be at least as fast as they can do it. So I had to take the approach during the whole of this project as being very applied in terms of my maths and being very pragmatic in that I had to use techniques which were quick, and you'll see some reasons why I didn't use Q-tensor at some points because I had to do it very quick and Q-tensor is sometimes very slow. So but it's good. I mean, it drives you towards different application, different methods to model these real devices. Okay, so let's start with some motivation. So Apollo has very nicely introduced a lot of this talk, and there is some crossover, and I'll mention the similarities and the differences as I go along. So here's a typical, very kind of stylistic idea of what a typical liquid crystal device is. Two planar, usually solid, inflexible substrates, usually made out of glass or plastic, and sandwiched in between these two bounding plates is an area of liquid crystal, and that liquid crystal, I'm only going to treat pneumatics, has a director N. Okay, so everyone in the room knows all about that. The important thing of this slide is to define these two angles, theta and phi. So theta here is the angle, next slide, theta here is the angle away from these bounding plates, so out of the plane of the substrates. And this is what I'm going to call the zenithal angle. It's often called the zenithal angle. And the other one is the angle within that plane of the bounding plates. I'm going to call it phi, and it's the azimuthal angle. Now, there are various devices, liquid crystal devices, in production at the moment. You can buy them in the shops, which use bistability of one of these two angles, or maybe even both. So I'm going to look at a couple of devices which have bistability in this zenithal angle, this out-of-plane angle, and another example that Apollo has already mentioned about bistability with this azimuthal angle, this in-plane angle. Okay, so here's some bistable displays. At least the bottom two here, I'm not sure about the top two, the bottom two here are available in the shops for you to buy. This one I'm going to talk about a little bit more, the ZBD, or the Zebedee device. This is now being used as you see here, a label for a shelf in a supermarket that can be remotely controlled. They can change the prices whenever they want, just from some remote office. as they often do. And I'm I'm not commenting because actually,
That's not the right word. I mean, right.
well, no, actually, one of the big benefits of this is maybe certain times of the day they want to put special offers on and sell more because it's lunchtime and they want to sell Coke. I don't know. I mean, that kind of thing. Okay, so I'm going to look at this. This is a device that came out of, in fact, the Ministry of Defence. So all UK citizens here, you've paid for the development of this device, and eventually span out into the Zebedee company. Okay, and I'll talk a bit more about that later. And in fact, Apala mentioned it briefly. Okay, so this Zebedee device, this is originally invented in '97. It's got a patent, a world patent there, dated '99. That's when it was granted. And this is actually the picture from that original patent. What they have here is the two substrates again, but one of them's patterned in some way. It has a grating. And the bottom grating here has a director alignment which is perpendicular to along the normal of this substrate, and the top one here has a planar or homogeneous alignment. There are two states here, and you can see this zenithal bistability. The angle in this plane perpendicular to the substrates, perpendicularly to the top substrate at least, there's two possibilities. One is a largely vertical configuration, and one's a kind of tilted configuration. The key thing here is that these two distortions differ fundamentally by the presence of these high distortion regions, these defects, or disclination lines, in fact, at the very close to the corners of this grating. Okay, so this back from '97 has been developed all the way up to the present day and is still being sold. It's now in shops all around the world. I just looked at their website this morning, and it seems that the Co-op supermarket in Slovenia now has these displays on their shelf edges. It's also being used in a larger format for display notices. So there's A4 versions of this that you can put around your office or your business and remotely update. Okay, the second display I want to look at is again something, you've seen this picture before in Apala's talk. It's called a post-aligned bistable display. Again, this is a picture from their original patent. And what they have here is, instead of having a grating which is two-dimensional, runs along one direction, they have these posts. And they're slightly tilted. They're tilted to break a degeneracy, in fact. And they're, again, two different states. This is a three-dimensional structure. Okay, and there is actually multi-stability in both the zenithal direction, as it's denoted here, but also in the azimuthal direction. In fact, we've had a lot of success in modeling this just in 2D, and the Hewlett-Packard, who invented this device, are using 2D code to actually simulate this and optimize it. Okay, and again, there are these high distortion regions at the corners of these, well, actually along edges of these posts. And this is the mock-up that Hewlett-Packard, the last version of this display. It's color, obviously. It's bistable, so this image is retained without any power being put to the display. You only have to put power on these displays when you want to change the image. Okay, and the final thing I want to look at is an azimuthal bistability. So this is, again, this is pictures from our paper that Apala mentioned. Again, I'll go through this in a little bit more detail, and we have these two states. Here's just some cartoon pictures, really, of the director structure for the two possibilities. There are other ones, but they're all degenerate up to symmetry. Okay, so here we have, and the dimensions of this, they're between 20 and 100 micron sized wells, filled with a pneumatic mixture, and then capped on top. So the liquid crystal is only contained, well, hopefully only contained in this well. And the shallowness of this well means it's a planar director structure, and I'll mention that again in a minute. Okay, again, there are defects, there are disclination lines. These disclination lines run through the, along these corners and through the cell. In fact, in both states, there are defects. So whereas the previous two cases, only one of the states had defects, here, both of the states have defects. And the bistability is caused essentially by locking these defects into different corners. just to answer a question before, all of this structure, the well walls, and actually the top and bottom of these wells is made out of SU8 with no rubbing at all, no treatments, and so with SU8 you get a degenerate planar alignment. It can be any direction the director, as long as it's in the plane of that, either the bottom surface here or the walls. Okay, so what we've seen is, here's some side views of zenithal bistability and a plan view of azimuthal bistability, and they all have defects, or disconation lines in fact, and so we presumably need a theory to allow for these defects. So I will, for the people who've been here since January like me, I'll give the 18th introduction to Q-tensor theory. Maybe I'll skip over a little bit, but here we go. So there's a director, everyone knows the director, which is based on the average molecular orientation. So within a ball of molecules we can define this director, and rather than just the director we could also define essentially a kind of standard deviation of the orientations around this direction, this average direction. And so this standard deviation is the S order parameter, and it's we've seen this before quite a few times, and it's a thermodynamic average of this polynomial of cosine theta. And the reason is of this form is that S equals 0, so 0 order means there's randomly oriented rods, so something like this, randomly oriented molecules, and when S is non-zero, there's a preferred direction. And so this configuration here would have a preferred direction, and so S would be non-zero. So when we're building a theory, we could have dependent variables which are just our order parameter and our director, but the more general description is actually to use a Q-tensor. So again, we've seen this before, and this is really a renormalized second moment of the probability density function. The first moment goes to 0 because this is a probability density function f, and L and minus L, the direction of the molecules, are equivalent. But the second moment gives you some information, and you can build this Q-tensor out of this second moment. It's the traceless part of M, essentially. Okay, and Q, the Q-tensor, is related to directors and order parameters in this way here. So we can define two order parameters, essentially the two eigenvalues of my traceless 3x3 matrix, or tensor, and my n and m are the eigenvectors of my Q-tensor. They're the directors. And we could, if we wanted, restrict this to a uniaxial system where there'd only be one distinguished director and one distinguished order parameter. But I will actually, all the way through, I'll use the most general biaxial order parameter, order tensor. Okay, so from these dependent variables, we could build continuum models out of just the director. So that's the famous Frank Ozeen-Zucker model. We could build just out of the director and an order parameter S. So that's essentially the Ericsson model of about 20 years ago now. Or we could build the Landau-de Gennes type of formulation by using Q as our dependent variable, and it depends on space and time. To do that, and the way I'm going to do it is formulate some free energy and then do essentially a gradient flow of that free energy just by looking at essentially a dissipation of rotation of directors. Okay, so you can also have all the variables as well, all the dependent variables like electric potential. So I solve Maxwell's equations as well at some point, so I'll need an electric potential as well. I don't ever use fluid velocities, in fact. So this is what I'm going to concentrate just now, but later on I will go back to the rather simpler version, which is the director model. Okay, so I'm going to skip through this because we've seen this lots of times before. There's a rather complicated elastic energy for the Landau-de Gennes formulation. There's I use an L6 term here, a cubic term in Q, to break the K1 equal K3 degeneracy that's inherent in the Landau-de Gennes formulation if you just use the first three terms. There are problems about this, and we heard about this yesterday, but I use it because I actually, in the end, do some quantitative measurements using Q-tensor theory, and I want to match to some experimentally measured K1 and K3. L4 here is a chiral term, and I don't use chiral pneumatic, so I set L4 to 0. In terms of, that's the elastic energy, there's a bulk thermotropic energy which tells you what phase you're in. I'm going to be relatively deep into a pneumatic phase, but here's the sketch of what an order parameter would look like as I vary temperature. At very high temperatures, I've only got this isotropic minimum where the order parameter is 0, and as I decrease temperatures, I get a first order transition with a metastable pneumatic state coming in here, and it gets what's called TNI. Both states have the same energy, and eventually as I decrease temperature, I get a rather large potential well where my system, the global minimizer of the system, would like to be a pneumatic. Okay, so I'm going to sit here, although obviously this is only a potential well that I can get out of if other things force me to. So maybe defects might force me out of this potential well, boundary conditions or applied fields. Okay, so if I was doing an Ericsson model where I just had my scalar order parameter S, then I'd model this, as you can probably see from this, I could model this with a quartic polynomial in S. Or if I've got a Q-tensor, the two invariants here are trace Q squared and effectively trace Q cubed, or the determinants of Q, and I can model it with this potential instead. I won't go into the diagram. Okay, so anchoring conditions are important. I've got a device with boundaries, so I need to think about what I'm going to say about the boundary conditions. I could put strong anchoring on this, so this means a Dirichlet condition in the director or S or my Q-tensor. In fact, I think pretty much all the time I'll put on weak anchoring, and so weak anchoring here, there is still a preferred direction. It's similar to strong anchoring in that sense, but I'm allowed to move away from it. If there's some other force dragging my director or my Q-tensor away from this preferred direction, it could move away at some energy cost. So in a director model, and I'll come back to this, then I can model this with the standard way of modeling weak anchoring through this type of term. There is a preferred orientation N0, but if I move away from that, I increase the energy, the surface energy. I can do very, very similar to the Q-tensor. There's a preferred Q-tensor Q0 at the boundary, and it would like to be there, the Q-tensor, so the eigenvectors and eigenvalues would like to be specific values, but it's again allowed to deviate from that. In fact, most of the time I'm going to use this rather more complicated surface energy, which is a planar degenerate. I told you before that the walls of the SU8 walls of my devices have planar degenerate anchoring. This just says that essentially the director would like to lie in the plane. Essentially this is fixing an eigenvector of the matrix Q. And so this is what this does. This is an energy, I guess, maybe first formulated by Mikhail Ozypov in one of his papers. And so this nu here is the boundary normal. And this effectively, if you choose your C1, C2, C3 correctly, this will fix one of the directors to be, prefer to lie along the boundary. Okay, so this is the kind of thing I'm going to use. I try, in equilibrium, I want to minimize the sum of all these energies, just work out the variation of this and solve the Euler-Lagrange equations. If I look at dynamics later on, what I'll do is a gradient flow. Essentially just look at the dq by dt equals the gradient of all my energy. Okay, so a little word on disclination lines. I've seen these before. So if you do look at a liquid crystal sample, a layer of liquid crystal, a pneumatic liquid crystal through cross polarizers, you see these rather distinct shapes here, these threads. Okay, and here is where there is a half disclination. I can't tell which one it is from this picture, but it's one of these type of director configurations. This is a plus half and a minus half, and I'll come back to that later when I show you some defects in cells. Okay, so this defect is, I just want to mention one thing. What happens as I go through the defect, and what I find is that I have essentially the eigenframe being fixed as I go from A to B, from this point to this point, but actually the eigenvalues exchange. And this is the only time really that eigenvalues will be changing. In the bulk of my system, the eigenvalues, the order parameters, would like to be constant. But near to defect, I'm going to get an exchange of eigenvalues. It's the only way of doing it. I can't get this from some director distortion. That's what Frank originally realized when he looked at defects. Okay, so back to my device. So this is the device that the experimentalists produced. Here's a one of the pictures of this device. And essentially what we have is this structure here, these well shapes, all made out of SU8, done by photolithography. We fill this with a pneumatic, well, we, not me. My friendly experimentalist fills this with a pneumatic liquid crystal. It's E7, a very standard liquid crystal. Very nice to work with. And then we cap it. And you can see here there should be no liquid crystal above these walls. There is sometimes, but we've now got round that. And we cap it with another layer of SU8. And the way to do this, it's a little bit tricky. Well, it's more than a little bit tricky. It's very tricky, is to actually cap this whilst your SU8 layer isn't fully cured and is wet. Okay, so our well depth is 15 microns, but the sides are between 20 and 100. In fact, 80 is a typical length of my well here. And so because of that aspect ratio, we get, and I'll show you later, I'll get the director in the plane of the cell here. Okay, so here's one of the first pictures we found from this. And you can see actually there is liquid crystal above the walls. This is the well, but there is liquid crystal. Oh, sorry. There is liquid crystal actually above the walls in this area here. So this is one of our first cells. It's now been rectified. We can get rid of that now. But you still see the idea. The idea here is that between cross polarizers, you certainly have two states. So here's one state and here's another. Look very different. And we can check as we rotate the polarizers that actually these two states here, which did look the same, are actually different. Okay, they look the same if the polarizers are aligned along the edges of the walls, but actually if you turn the polarizers a wee bit, then you can see that they're actually different states. Okay, something else I want to say there. What we actually found, so these are the two states that look the same, this one here and this one here, and as you rotate them round, we found that they actually look different. The black lines along this side and the black lines along this side here, and these are effectively the two diagonal states that Apala mentioned, where the directors aligned along diagonals, but two different diagonals. And this one in the middle is where the directors aligned along a vertical between the two sides. Okay, so this is all experimental results. I'll show a lot of experimental results and hopefully show you some theory as well. The theory, which seems to have gone slightly crazy, but the director structure, if we're modeling this, what I do is I do a Q-tensor theory. I effectively have a box, and I throw a liquid crystal in there and let the Q-tensor solver try and find an equilibrium state. So a few things to mention about this. The boundary conditions, as I said before, all that happens at the boundaries is that one of the eigenvectors of my Q-tensor would like to be parallel to the boundary. So I've done this in two different ways. The first way is to just take a 2D slice. Actually, both ways I'll take a 2D slice. But I allow my director to come out of plane. My director is three-dimensional. It's allowed to have any orientation of eigenvectors. The key thing is if I start with an in-plane director structure as an initial condition, it's not going to go out of the plane. There's no perturbation out of that plane. And so we thought that was a slight limitation to our model. Of course, we do have the possibility that the director comes out of plane. And so what we did was we set up a system where there's an effective surface anchoring from the top and bottom surfaces. And I just had a penalty term that I allow the director to go out of plane, but it costs some energy. Okay, that's an extra energy term. And then I can actually put in a director initial guess or a Q-tensor initial guess that actually contains some out of plane component, but it actually goes back to an in-plane configuration because of the restriction of the upper and lower surface. Okay, so let's have a look at some results. So here we have the experimental picture here with a kind of cartoon that we drew at the time. And here we have the order parameter, well, the largest eigenvalue. The largest eigenvalue of Q is drawn here. The dark points here, very similar to a Apala's picture. This is dark means a lower order parameter. And here's the director structure. You see the two diagonal states, one here, and this actually is not this is where the director largely lies horizontal. Okay, so we have disconation lines running down through the device, but we also have, you might notice, some other regions of high distortion at the other corners. They're not strictly defects, but they're other regions. One thing I should note here, and I'll come back to this, is I've rounded off the corners slightly. We're modeling a real device here. We can't have sharp corners. Well, the experimentalists tell me you can't have sharp corners. So I put in a small radius along this corner here. Okay, so just coming back to that, I can round the corners off however much I want. And actually, most of these were done experimentally as well. And what I see is with very sharp corners, as Apollo saw as well, there's a defect right at the corner there. It can't get out. And in fact, there's also a defect here. But as soon as I round off these corners, the defect pops into the bulk of the liquid crystal. It doesn't move very far, and I can go all the way to a circle, and it stays where it is. Of course, in the circle, I now have a degeneracy. My two defects have to be diagonally opposite along a diameter, but they could be anywhere at all. It's the fact that I've got corners that stabilize this system. So I can see this if the stabilization by corners, if I think, oh, just one thing there, here's my half defect cartoon, and I can see it exactly, that's what we've got here, a half defect. I can switch from one state to the other, as Apollo did, simply by applying an electric field. Okay, so in the Q-tensor model, I solved Maxwell's equations in this whole area by putting essentially electrodes running diagonally outside the cell. And I can do this, for many different shapes. So I can do it as a function of my corners being rounded off. Okay, so let's have a look at that. What happens is, I see, so here is elastic energy versus time as I've turned my voltage on and my whole system's going to rotate. Elastic energy is going to go up because I'm going over an energy barrier between two stable and elastically stable states. When I've got relatively sharp corners, I've got a very large peak. And when I've got rounder corners, I've got a smaller peak. This is not quite a circle. It's very nearly a circle, but it's not quite. For a circle, there'd be no barrier at all.
Excuse me, Nigel.
Yeah.
Where are the electrodes, did you say?
Okay, the electrodes in this, because I want to turn my director from this direction to this direction, I effectively have an electrode. The field's got to be applied along this direction. Okay, so my actual computation region for the electric field is much larger. And I put an electrode, if I can show this. I put an electrode here, and I put an electrode up there. Okay, so then my field's going to run from this perpendicular to this electrode over this way. Okay, so the field will mainly run in exactly the direction of this final director. I mean, obviously I'm solving Maxwell's equation, so it's not exact like that. Okay, so I've got this energy barrier. It's nice to see that. The thing I then looked at was the fact that, well, if I forget all the Q-tensor, it's very computationally intensive. And unfortunately, I was taking essentially, well, maybe my computer was pretty slow, but to compute all of these structures and the switching here was taking a few days. And Carl, being the good experimentalist that he is, could make all these things and test them all really quickly, and he was beating me to it. So we had to find a way of beating him, and the way we wanted to do it was go back to a director model. I know I've done director models many times, I can solve these really quickly, but can we do this? Because of course we've got defects here. Well, let's have an analytical way of doing this. If I look at a director model in a, just for equilibrium with no electric field, just thinking about the static states, a director model with an equal elastic constants approximation just is actually solving Laplace's equation, where phi here is the azimuthal director angle. Okay, so let's try and find out if we can do all this. I'm just solving Laplace's equation in a square. Well, let's do a slightly simpler system. Let's think about the liquid crystal in this wedge. So I'm thinking about this as a corner. So in this wedge here, I've got certain director azimuthal angle anchoring on this surface and this surface, and there's a wedge angle beta 1. Well, this is a relatively standard conformal mapping, and this is the solution. This is an infinite area of liquid crystal. It can't see anything else up there, but this is the actual solution. And from this, I can do an awful lot of things. I can work out the energy. And this energy depends on beta 1, which is the wedge angle. And it also depends on n here. Now, n is the number of rotations it's related to the number of rotations that the director goes through from going from this surface over to here. Okay? So I can go, this rotates in a positive sense, this one rotates in a negative sense, and the different n relate to that. I could rotate many times before I eventually get back to here. This is actually very similar to some work that Apala did in her thesis, working out these winding numbers going from one surface to another. These two I've put out here because these are the lowest energy solutions. So I can plot this energy actually as a function of both beta 1 and n, the number of rotations. Just a couple of other things. This is the wedge angle. I've got to, when I integrate my energy, I've got to integrate in a finite region or else I get an infinite energy. I've also got to take out a small defect core here, which again gives me this kind of log of r over epsilon, just to make the energy finite. Okay, so here's a plot of the energy versus the apex angle, this wedge angle, for lots of different values of n. Up here, n equals 3, my director, as I go from one edge to the other, rotates about 3 half turns. And n equals 2, for instance, is this line here, and it rotates a bit less. And eventually I realized that the two lower energy solutions are either the n equals 1, it looks like this, it's pure splay, or the n equals 0, and this looks like bend. And the crossover, as you might imagine, the crossover happens at pi over 2, and this is exactly the situation here. So sitting at this pi over 2, which is exactly what the corners of my box are, I can see that actually what I've got are two possible configurations, just pure splay or pure bend. And so I look back at my box and I realize that yes, in this area here, that's exactly what I've got. My director is given by essentially this configuration. And at this corner, I've got this bend. And so I can specify exactly what my phi is, my azimuthal angle. It goes from pi over 2 to 0, and 0 back to pi over 2. And the other state is slightly different. They've swapped round, and now I go from pi over 2, increasing my director angle to pi, and then I go back from pi backwards up to pi over 2. And so there's my characterization of my two stable states. Here they are, and the boundary conditions now, in a similar way to what Apollo was doing. I'm just fixing the director, though. I don't have to have an order parameter here. On the two sides here, it's pi over 2. On the top, it's pi. And the only difference between the two states is that the azimuthal angle is either 0 or pi. And actually, in fact, what we did when we switched these things using a Q-tensor, what we saw was that this defect just moved along this bottom line from A to B and eventually ended up at B. And we can mimic that with conformal mappings. It's not a very easy one. You have to use the Schwarz-Christoffel transformation, so it's not so analytic, as it were. But we can also investigate the transformation between these states by actually picking up this defect and moving it. So I start at A, and I can move it to this point here and just set the boundary condition to be pi here and 0 here. And I gradually move it. And at each time, I work out the energy. So I can calculate the energy. It's one integration to do that. And here I see there's a great big energy barrier between these two states. I can go from one to the other as long as I can get over this energy barrier. Okay, so let's go back to something rather than azimuthal stability. This is zenithal stability. So here's the Zebedee device. It's got a grating. So Parla showed a picture very similar to this. It's got this two-dimensional grating structure. It's got these two possibilities, and you switch from one to the other with voltages, positive or negative voltages, switches from one to the other. What we decided to do, we had loads of success with this azimuthal angle. We decided to try and... The problem with this device, it's great, but we don't know what's going on in there. This is just a kind of cartoon of what exactly is going on. You can do numerical simulations of this, and you find it. Unfortunately, optically, we just look from the top, and it's very hard to distinguish what's actually going on. Apollo very briefly mentioned that when she had this solution, she said it probably wasn't visible optically. So what we decided was to take this whole thing and put it on its side. Okay, so now we have our SU8 kind of structure. We're going to fill this channel with liquid crystal, stick a cap on top, and look at it from the top down. And then we'll see the full director structure. We can vary lots of things like the channel width and the pitch of these things. We can also vary the, and I'll show you some pictures of the skew gratings as well. And we fill it again with E7. Okay, so here's some pictures. Here's the experiment. You can actually see some transmission contrast between different areas of director orientation. Here's the theory, and at this point here I'm actually doing Q-tensor theory. And here are the kind of cartoons taken from this theory of the director structures. Here's a relatively low distortion. Here's 2 high distortion regions. Okay, so it looks like we match pretty well, experimental theory. And again, the bistabilities occurred because exactly in these corners here, we either have kind of a bend solution or a splay solution. There's also some possibility of having multiple rotations forwards and backwards as well, gives you all other states. And we can do lots of different wall geometries. I'll just flash up some pictures of some experiments here. So again, we can have these grating on both sides. We actually get some very nice contrast between 2 different states in this case. And we can have the gratings out of phase, and we again get lots of different things. Okay, so the theory matches with the experiments really well. This is just the static theory. We can start blazing the grating, so making them asymmetric. And this helps because you break a degeneracy in the defect position. But the key thing here is that for some systems, you get very little contrast between 2 states. There's a very bright state and also a very bright state, even though the director here is very different. But when you can do this kind of optimization of these parameters, then you can find some states. This blaze state here is very good contrast. Okay, so what Carl asked us is to fully optimize this system. We've got so many parameters to change in the geometry in the liquid crystal. And using Q-tensor theory, this was very difficult. He also did switching between the states, and that's when we got into difficulties, because we can switch between this green state and the red state, and here's the switch. And what you see is some rather interesting, what look like disclination lines. We find out later they're not. And eventually you switch into this dark state. And you can switch back, and it looks even worse. Some very interesting kind of reorientation walls, in fact, as we go from one state to the other. So the problem was that Q-tensor was slow. Well, certainly my implementation of Q-tensor simulation was slow, and far too long for commercial device optimization. So we had to be a bit pragmatic here and go back to our director model. And we did a very simple thing. We did the director model. We had some elasticity, one constant elasticity in 2 dimensions. We had a very simple electric field term. I didn't solve Maxwell's equations in this. I could have, but it doesn't make much difference. And I've got this, this is the rotation of the director angle theta. Okay, so I've got a elasticity, an electrostatic torque, and a director rotation. I need weak anchoring. I'll come back to this. The weak anchoring I have says that the surface torque, as it were, this is the surface normal, has to balance with some change in surface anchoring. And a very simple Rapidi-Popper kind of term. So here's some results. We start from this planar state. So here's an experiment. Here's my theta model. And I'll come back to this, but there are no defects in this system. I can't have defects. They cause singularities. Here's the theta model's transmission. I can just simply model how the optics would look in transmission, and the Q-tensor transmission as well. Okay, so that's great. We can do the static equilibrium state. Kind of knew that already, to be honest. But even better, we can do the switching. So here's the experimental result. We turn a voltage on. Lots of funny things happen, and eventually we turn it off after this state. Here's the director model, and here's the Q-tensor model. Almost exactly the same, certainly qualitatively, and actually we've got some good quantitative agreement as well. I'll come back to exactly what's happening in these loops just in a minute. The final state then, just let the voltage come off and it all relaxes back to the other state. Okay, so what's actually happening here? So we start out, if we start out in this orientation here, then on one side of the grating, the director is pointing upwards in one sense, and on the other side of the grating, it's pointing in the other. As soon as I turn an electric field on, my directors here will like to go vertical, and they go in this clockwise sense, and these ones go in the anti-clockwise. And so we get just regions of different director orientation between pi over 2 and minus pi over 2. And these are just reorientation walls, pi walls. Okay, but they're not stable. They have a line energy. And so what happens is they then, because of that line energy caused by the elasticity, they then reduce. And in fact, you see this smearing out of the distortion along the surface, and eventually this loop collapses. So as time goes on, my loop collapses. This is all the theta model, the director model. So as I said, there's some quantitative comparison here. The numerical results are this dashed line, and the experimental results are the solid line. And as time goes on, I see the x-axis coordinate of these two defects look fairly similar. Not bad, really, I think. And what's happening right at the surface here, we have these loops, and as soon as the field goes on, there's these distortion regions. They're not defects. They're not disclination lines, because I can't have disclination lines in this model. And so the disclination actually sits slightly below the surface. Eventually they collide, and then they relax back into the minimum of this grating. Okay, so nearly there. One thing is we look back. Actually, this is stuff I've done whilst I've been here. We look back at my original model of the azimuthal device. So here I've just done a director model again. But I made weak anchoring in there. And again, I found, just as Apala mentioned, in a Q-tensor model, you can find bistability even though there are no defects in here. And of course, if there are no defects, you go back to your original assumption of saying, oh, well, there's defects, I need a Q-tensor model. You don't need a Q-tensor model. You can just use a director model. And the defects effectively lie outside the surface. They're like virtual defects. And in fact, we can do switching. So this is just a very quick run I did last week. I apply an electric field. My director's in one diagonal. I apply the field vertically in this sense. And then I let it relax. And because of some tiny amount of pre-tilt I put on the surfaces, it relaxes back into the other bistable state. So this is all just director model. It runs, well, that ran in, I don't know, 10, 15 seconds. So at last we can actually do some optimization of device geometries because we can get this running. This is all just on my laptop, in fact, running fairly quickly. Okay, and just in summary, so I've done some, so compared to Apala, who's done some more molecular scale models and some very good analysis as well, I've gone slightly different routes. I've done some Q-tensor models, but finally realized that actually Frank was right all along. You just need a director model to do an awful lot of these things anyway. And what you see down the experimental microscope in terms of what you think are defects could well just be high distortion with no actual defect there. Okay, and I'll finish that.
Very much, Nigel. Again, plenty of time for questions.
Yeah, a couple questions. One is, why is the Q-tensor model that much slower than the director model? You were saying days versus seconds?
Yeah. I mean, maybe I've not implemented it right, but I mean, the key thing is you've got a director core there, which is many orders of magnitude smaller than your device. So, okay, so if you have a device which is, I don't know, 0.1 of a micron, then you can do it really quickly. The point is, I'm trying to model 80 microns squared, and I've got a defect core here which is very, very small. And whatever, I use finite elements for this, I've got a load of finite elements right at that core. And because of that, that slows up my whole routine.
So because you're trying to model what's happening inside the defect core, you need a length scale as small as the defect core.
At least there, yeah.
So you need some huge number of
well, I have larger elements in the bulk, so I've got a non-uniform grid. Otherwise, that would really take a long time.
Yeah, okay. I see. And I guess for another question, when you were doing the numerics and you get the energy barrier,
yeah,
right? And so you know what the state looks like as it's passing over the energy barrier,
yeah,
right? And so is that something that can generally be characterized by just a few parameters, like a defect that's moving or?
Yeah, well, we started out, actually, because of the problems with Q-tensor, we started out with a very small box. I think it may have been, yeah, it might have been 0.1 of a micron, because we could solve that really quickly.
Mm-hmm.
What happens there is the defect moves from corner to corner. Well, only one of them has to move. But actually, in a very small device, they both move. One of them kind of moves out and then back. And this other, the one that actually does have to move to a different corner, comes way into the bulk of the cell and back out. Okay? And then we started having more computer power and actually making it bigger. And we realized actually the defect just runs right along that surface. And it prefers to, I mean, it's easier to melt, I think, essentially, at that surface. And so it runs right along the surface. And that's what led us to actually just doing a director model where the conformal mapping, we can just run that defect along that surface. So we think that's a good model.
Thank you.
In what computation you see this loops forming? I mean, how often this happens?
Always, always.
So it's during switching you see these loops?
Yeah.
So your static configuration is smooth except corners, but during switching you see loops? Is this how it works?
Well, actually, as I said, these aren't actually technically disclination lines. These are reorientation walls. Okay, so the director just over a small, I mean, the thickness of that loop there is determined by the strength of the electric field. So my electric field is telling me to point this way or this way, and I've just trapped a reorientation region. It's a pi wall. Okay. There's no singularity in my director. My director just rotates by pi. It's confined to a rather small region, that's all.
So for structures like that, is the neglect of flow effect not a problem?
Can't start talking about flow. Oh, I have no idea. I have no idea. To be honest, I'm happy that it looks like the experiments. You know? So you kind of go, well, maybe flow's not important.
Tim, I can see.
Yeah, right at the end you were sort of talking about device optimization, but so you've probably got some optimization criteria. I mean, you know, the process of engineering optimization is
Sure.
a very,
Yeah.
you know, it's not in many cases, if you want to optimize some engineering process, that one computation does indeed take a long time.
Yeah. Sure.
And so we have special software in order to do that, and I wondered, what are your figures of merit for optimization, and had you thought of using professional sort of optimization rather than, if you like, rather than just say, gosh, I need to get my simulations as short as possible, you know, have
Oh, I see. Okay.
fewer simulations, but do some interpolation and you know what.
Yeah, well, I mean, the difference in simulation time between these two methods is a couple of orders of magnitude. That's got to be good, no matter what. I mean, you know, the optimization of these, I mean, the optimization, the real optimization, the goal function, it might be a combination of both switching and optics. More likely in a bistable display is optics, so contrast and if you're reflecting device, reflectance. So those things are most important because normally in a bistable device you're not too worried about the switching speed. So, and actually having such a huge energy barrier is not good for switching, yeah? So normally it's about optics. So those are fairly well characterized in terms of the optimizing function.
I saw Epifanio at the front, and then we got Dan in a minute.
In the pi inversion wall, do you have any indication on how the length of the wall decays in time?
Yeah, okay, I've not shown it, it's in the paper. We actually measured both length and area of the loop, you know, in time. And so, yeah, that's, from memory, I think the area varies linearly with time. But it's in the paper, I can show you that later.
You mentioned K3 not equal to K1, and first off, what is the ratio that you're worried about, and does it really show up, or is that an academic issue?
Well, so the ratio, I honestly can't remember what the ratio for E7 is. It's between 1/2 and 2. I mean, most liquid crystals are between 1/2 and 2, but I can't exactly remember what it is. We used it because you saw the last pictures. We had great comparison to experiments. Without that, it would be less great. It's not optimized. We've not fit any kind of parameters here. We've just put the parameters for E7 in and see what happens.
So is E7 K3 and K1?
They're not different. I just can't remember the ratio.
I understand, so but that does give you a distinct difference.
Yes, yeah, absolutely.
One quick one then from Claudio, and then we must move on.
I was wondering what happens if you have a rectangular box rather than a square one.
Yeah, okay, so rectangular boxes, we tried lots of things. So the pattern actually has hexagonal boxes. And hexagonal boxes are great because the contrast is far better. We tried rectangular boxes, and as long as, what happens is, as long as your defect moves along the short side, that's great. If it tries to move along the long side, it's not good. So yeah, I mean, the switching and well, actually, even the stability of each state is affected by that. Paula did some work on that in her thesis, I think. Is that right? Or maybe afterwards. Yeah, it was cubes actually, so even better. But yeah, I mean, the stability is affected and the switching is affected. Yeah.
Okay, let's thank Nigel.